This week we're looking at Unit 1 and we're going to look at lessons 6 through 11. So it's a lot to go through. We're going to talk about text, we're going to talk about images, we're going to talk about compression, and we're going to talk about IP or intellectual property. So kind of remember the overarching theme here. Unit 1 is about digital information. It's this idea that computers can only deal with numbers. And last week we learned about binary, right? So we know that under the hood, everything that goes on with a computer is getting broken down into zeros and ones. So computers are really this giant machine that deals with abstraction, right? We write programs and applications to abstract all of this 0 and 1 calculation going on to simple things that we can understand, right? We just try to make it simple for people so that the computers are actually useful. But we need to remember that everything in our world is analog, right? The sounds that come out of our, voices, the pictures, everything like what we see, what we hear, it's all analog. But we have turned into a digital world where we are digitizing that information, breaking it down to these zeros and ones, and then we can use them on our phones, on our computers, and all these different devices that we have. So this week, now that we know about binary, we know about the zeros and ones, we understand this idea of round-off errors and overflow errors. We're going to start talking about how computers display text, how they display images, how we can compress data so that we can send it across the internet more efficiently, and then finally this idea of intellectual property. Who owns all of this information, all of this digital information that's being created? Who owns it, right? It's kind of a problem in computer science these days. So you will see all of this is going to open up on January 12th. It is due by January 18th. There is only one assignment this week. It's your Cornell notes for lessons 6 through 11. So if you go to that assignment, you will get a link to this document. Your job as you watch this video is to fill all of these pages in with notes. All right? So as I go through this video, again, I'm going to kind of give you the answers to these. So you just need to follow along, pause where you need to, fill in the definitions and the answers to the questions that I'm giving you so that you can kind of show me that you're watching these and understand this. So we're going to start looking at the slides. All right, so we're going to start with lesson 6. This is talking about representing text. The idea here is that when we look on our screens, when we see an A, or if we see a exclamation mark, or if we see a hashtag, we need to understand that that's a form of abstraction. Behind the scenes, it's really zeros and ones. So this kind of gets into your first couple of definitions, right? The first one is ASCII. Which I know it's kind of cut off at the bottom of your screen here, but ASCII, ASCII. It stands for American Standard Code for Information Interchange. You don't need to know what it stands for. You just need to know ASCII. ASCII is a standardized character encoding system that assigns a specific number to every letter, digit, or symbol in our alphabet. So the idea here is like this capital A, right? Your computer doesn't know what a capital A is. It sees a capital A as this 1 byte or 8 bits of zeros and ones. 0, 1, 0, 0, 0, 0, 0, 1. That is the decimal number 65, right? So ASCII is basically this coding scheme, right? It says A is 65, lowercase a is 97. We can use this to kind of convert binary that we see to the letter that it represents, or if we're asked on the AP exam, like, what is the binary for capital R, right? So they would show you this table. You would have to understand, okay, capital R, that is represented by the decimal number 82. 82 in binary is 0, 1, 0, 1, 0, 0, 1, 0. So you'd be looking for this as a multiple choice answer. So again, this whole concept, ASCII, it is one form of character encoding. There's different ways to encode characters. ASCII is the only one that we cover in this class. Character encoding is just a system that assigns a unique number to each character so a computer can store and process that text as numeric data. Right? So this text, even though we read it as text, it's abstracted so we can read it, we understand it. The computer needs this to be numeric. So we use this encoding system, this idea of character encoding, to assign numbers to letters so that we can convert those decimal numbers to binary. Again, this is abstraction, right? This idea that I'm going to read the text, how's it going, right? You, as computer science students, understand this is ASCII, which is a bunch of decimal numbers, and those decimal numbers are broken up into binary. So we are abstracting this, right? The average person doesn't need to understand the zeros and the ones or this encoding. They just need to be able to read the text, right? That's a form of abstraction, this process of hiding lower level details so that we can work with the ideas in a simpler and more meaningful way. Right? We're trying to take something complicated and make it simple. That is abstraction. It's like when you're driving a car, right? You don't need to understand how the transmission works, how the steering works underneath the hood. You just need to know if I turn the wheel, the car turns. If I step on the gas, the car accelerates. If I step on the brake, the car slows down. Right? That's abstraction. You don't need to know how it's working behind the scenes. This is the same idea. You don't need to know these zeros and ones. You don't need to know character encoding. We are going to abstract all of that, make it super simple, and just show you the text. So why do computers need a system for representing text with numbers? Again, computers only work with numeric data. So every letter, every symbol, every punctuation mark must be assigned a number before it can be stored or processed by a computer. ASCII helps us do this. It's one way that we can do this. It provides a standard list of characters paired with those unique numbers. Right? That chart that we were just looking at. This ensures that different computers store and read the same characters in the same way. And then lastly, how is representing text an example of abstraction? Well, representing text is an example of abstraction because users read and write characters directly while the computer works with numeric and binary versions that are hidden from view. Right? This allows people to communicate without needing to understand how those characters are stored internally. All right, so that's pretty much lesson 6, right? We're going to look at lesson 7 now. This is this idea of black and white images. It gets us into a couple of different concepts. So the first one is analog data, right? We live in an analog world. Analog data is data with values that change continuously or smoothly over time. Examples of this are music, colors of a painting, position of a sprinter in a race, right? When we hear sound, it's continuous, it's smooth. When we look at, the world around us, the colors they're smooth, they're continuous, that's analog. Digital data is different, right? Data that's digitized has been changed, so it's very discrete through a finite process of possible values. And there's some examples here. This is an image of, a swan. It's very, clean. It's clear. We can look at this and we know what it is. We're going to say this is like the analog image. If I'm going to digitize this, I have to do something called sampling. All right, sampling is the process of measuring an analog signal at regular intervals to create a digital representation. So what this is showing us is that, okay, this is our analog image. If I'm going to convert this to digital, I need to determine a sampling rate, meaning how often am I going to take a snapshot of this image to create a 0 or a 1 out of it. So in this example down here, they decided to say, okay, we're going to take 64 snapshots, which is this 8 by 8 grid. Each one of these, we have to determine in that snapshot, I'm essentially saying I'm taking a snapshot of just this part of this picture. Am I going to show this as white or black, right? They chose white. The second snapshot, a little bit over, white. Even the third one, they said it's white. Even though technically a small part of it really is black, I can't make that determination when I'm doing my sample. I have to choose, is it white or is it black? So they went white. And you can kind of see as they kept making this decision across all 64 of these samples, it does create an image. It's just not very clean. It's not very clear. Right, so each one of these little squares, we call this a pixel. It's the smallest unit in a digital image, and it represents a specific bit or a group of bits. Resolution, which is your last definition for this lesson, is the number of pixels used to represent an image. Right, so we have, 64 pixels in here. The resolution, in simple terms for it now, we can just say it's 64. The sampling is this idea that I took this analog image and I took 64 discrete finite values, right, samples of this image to do my best to create a digital representation of that. What you see as you kind of go through this, if I want to make my digital image better, maybe instead of taking 64 samples, I could do a 16 by 16 and take 256 samples. Right? That's going to make each one of these squares exponentially smaller, and now I can even more closely match what this image actually looks like. The point is, we're limited in how many bits the system has. We're limited in how many samples we can do, so we can never get it 100%. Right? There's going to be some data loss when we're doing this, but we can get it pretty close, right? Especially with modern computers. This is the same thing just with sound, right? This like sound wave in an analog world is very continuous, very smooth. They took 6 samples from this sound. So instead of this being a nice continuous sound that maybe some music that you were listening to, it would get broken up into 6 very distinct notes. Right? So it's going to sound choppy. Now if I wanted to increase my sampling rate, I could. It would increase the quality of my digital copy from this analog signal. But again, the trade-off is the more I sample, the more data I'm going to use, which is generally considered kind of a negative. So we want to find this balance between what is the right sample rate to get a quality that I can live with, right? And it kind of changes based on what the situation is. We'll get into that in a minute. But for lesson 7, kind of looking at those questions, how does sampling help a computer turn an analog image into a digital one? It helps by dividing the image into small sections and deciding for each section whether it should be represented as a black or a white pixel, right? This allows the computer to store the picture using bits. Why does sampling more frequently produce a better digital approximation? Well, sampling more frequently produces a better digital approximation because smaller sections capture more detail from the original analog image, making the final digital version just clearer, right? More recognizable. Even if I went from 8 to 16, I could go from, a 16 by 16 to a 32 by 32 or 64 by 64. At some point, I'm going to get to the point where this is really close to that analog image. But that's lesson 7. So now looking at lesson 8, we're talking about color now. And again, we're dealing with bits and bytes. RGB should be familiar to you. We use this when we were coding to create colors within our app. The idea behind RGB, it stands for red, green, blue. Each one of those colors, red is 8 bits or 1 byte, green is 8 bits or 1 byte, and blue is 8 bits, 1 byte. So this gives us a lot of variation in the colors that we can use. So RGB is just a color model that represents color by combining different intensities of red, green, and blue to produce a wide range of colors. When we're talking about color depth is a number of bits used to represent the color of a single pixel. I'm going to show you an example of this in a minute. But as far as your definition goes for color depth, just know that it's the number of bits used to represent the color of a single pixel. And this really determines how many different color values can be displayed. The bits per pixel, again, I'm going to show you this in code.org. That's how many bits are assigned to store one pixel's color information. So what they're getting at here is the more bits per pixel that you have, the more shades of color you can show. And then lastly, you have this color gradient. That's the smooth change from one color to another. And again, when we're going from analog to digital, we have to approximate this. So the color gradient really is a smooth change from one color to another that must be approximated using discrete pixel values in a digital image. So let's look at this in code.org really quick. You have access to lesson 8. You can play with this if you want. What I have right now is a 3x3 grid, and I'm saying my bits per pixel are 3. All right, what this, if you look over here, the pixel format, if I'm going to use 3 bits, that means I have 1 bit for red, 1 bit for green, and 1 bit for blue. So really what this is saying is I can combine red, green, and blue to make different colors. Each bit, because this is binary, can only be a 0 or a 1. So if I made all 3 bits 0, I get the color black. If I make all 3 bits 1, I get the color white. So let's look at this second row. What I can do now is I can say, okay, I want a red pixel. So I can turn red on, green off, blue off. I get red. I can make green by just turning the green pixel on, or green bit, or I could make blue by just turning the blue bit on. Right? And then I really only have like 3 other options. I can say, okay, let's turn red off and turn on green and blue. I'm going to get that light blue color. If I turn red on, green on, but leave blue off, I'm going to get yellow. And if I turn red on, green off, and blue on, I'm going to get this purple pinkish color. Right? So I'm using 3 bits per pixel. And again, we're talking about how the number of shades of color that we can create changes with our bits per pixel. So what you're going to notice, I'm going to change this to 6. So when I do that, what you notice is now I get 2 for red, 2 for green, 2 for blue. And what I'm able to do now, before I could just create 1 shade of red. But now I can start to, maybe I got 2 for red. So I'm going to turn 1 red on, 1 off, and then I'm going to leave green and blue off. And I get this color red. If I turn the first red off but leave the second one on and leave the rest off, I get a darker shade of red. And if I just turn both reds on and leave everything else off, I'm going to get this kind of standard red. So you can see now that I have 2 bits per pixel, I can create more shades of red. It's the same thing for blue. And I'm actually going to switch these just so they go kind of from dark to light. So for blue, or sorry, for green, if I say I'm just going to turn 1 green on, here I'm going to turn the first green on, leave the second green off. Right? Again, with the green, I can make a dark, a medium, and a light color green. Same thing for blue. Right? I can kind of go between those different shades of blue. Again, this is just pointing out that bits per pixel, the more bits I use per pixel, the more shades I can create. If I change this to 9, I would now have 3 for red, green, and 3 for blue. Right? So, like modern computers, we can start going up to all different kinds of numbers. I could go with 15 bits per pixel. Now I'm going to have 5 red, 5 green, 5 blue. This kind of exponentially increases the shades that we can use within there. But that's really kind of what you need to know for color images. So like, how does RGB values allow computers to create many different colors? It can create many different colors by assigning each pixel separate intensity levels for red, green, and blue. Right? We combine these 3 values to form a wide range of colors. How does increasing bits per pixel change the quality of a digital color image. That's kind of what I was just showing you. We're going to get more shades when we do that. So increasing bits per pixel improves the quality of the color image because it provides more possible color values for each pixel. I can create more shades of red, more shades of green, more shades of blue. And then why do digital color gradients look less smooth than an analog one? Again, this idea of gradients kind of gets into, let's see if I have the picture. I don't think I have a picture of that, but you know, here, let's look at this. If we're looking at this image, there's some gradients going on, right? It's kind of going from like, you know, dark to this, you know, red. It's really smooth. But if I were to zoom in on this, right, at some point you actually see this little grid pop up. These are the different pixels. Right, and again, this is RGB, so this is 8 bits per pixel, and you can see that even though each pixel is only a single color, there's so many shades of orange that we can create, right, within just this kind of zoomed in view of this, that when I zoom out, right, at some point my human eyes can't see the difference, right? It's good enough. This is not exactly what it looked like when this person was looking at this and took this picture. But it's so close because we have so many bits that we can get it really close, right? So this idea of digital color gradients, when we really look at it, they're not smooth, right? They're finite, they're defined, but we do the best we can with this. All right, so that, you know, again, this idea of abstraction. You know, when we're looking at digital images, right, we have this analog image, we're going to sample it, we're going to create this pixel layer, and then each pixel is going to get converted to a binary layer, zeros and ones, right? This is abstraction. You don't need to understand the zeros and ones, you don't need to understand the pixels, you don't need to understand what the sampling or the sampling rate was. You just get to see the image, right? It's abstraction. We're taking something complex and making it simple. So kind of with this, we're going to talk about compression. And there's two different types of compression that you have to know for this. The first one is lossless compression. Lossless compression reduces the number of bits needed to represent data without losing any information, right? The important part with lossless is that you do not lose any information and the process is completely reversible. So we're going to look at code.org again. So I need to switch to a different lesson. And I'm going to kind of show you how lossless compression works. So there is this lossless compression widget. And the idea is I can choose, you know, some of this text. And what I want to do is I want to try to compress this. So you'll notice that there's the text over here, and there's a dictionary. Down here is my compression rate. Right now it's 0. So what I'm going to do is kind of show you how lossless compression works. The idea is I'm going to look for patterns in my text. So for example, I see that underscore THE underscore. This is repeated a few times in here. So if I add this to my dictionary, you'll notice that over here it replaced, anywhere I had underscore THE underscore, it replaced it with this little sun symbol. Right, so while this was 5 bytes, right, each character is 1 byte, which is 8 bits. I took those 5 bytes and I reduced it down to 1 byte. So I'm starting to get a compression rate here. It's saying my compressed text is 85 bytes. So this right now, the way I have it, this is 85 bytes. I have to include my dictionary in this because I need to know how to get this back. So my dictionary, just this one line, is 6 bytes, which is a total of 91 bytes. Now originally, before I had changed anything, my original text was 93 bytes. Right, so just making this one change, I've gone from a message that's 93 bytes to a message that's 91 bytes. And what I can do is I can keep looking for patterns in here. So I see TTER underscore, that helps me. I'm down to 30%. What I notice now is there's PI with the umbrella and PA with the umbrella. That seems to be happening a lot. So I'm going to say, okay, PI with the umbrella, and then I want to do PA with the umbrella. So I'm down to 37%, and then I've noticed that this snowman with the snowball repeats a few times, so I'm going to go ahead and add that as well. So you can see I got about 40% compression on there, right? This is lossless compression, this idea that I'm going to find repeating patterns inside of my text, my images. Remember, this is all zeros and ones at the end of the day, so they're looking for the ways the zeros and ones repeat. And they convert those to a single symbol. And then they replace that original text with the symbols. So if I was going to send this message, I would have to send this compressed text along with this dictionary, because this dictionary will tell the receiving computer how to undo that compression. But while that text is in transit, right, while it's going from one phone to the next phone, I was able to send 56 bytes instead of 93 bytes. So I saved about 40%. That's a good thing, right? That is lossless compression. So when the receiving computer gets it, it just starts kind of undoing this one line at a time, right? And eventually it gets itself back to the original message, which was my point over here. Lossless compression. When we are doing this, the important part to know with lossless compression is that no data is lost and it is completely reversible, right? So kind of looking at the Cornell notes, you have lossless compression, which, this is your definition, this process for reducing the number of bits needed to represent something without losing information, and understand this process is completely reversible. With this, we get that dictionary or that key. That's just the set of symbol to text mappings that tells the computer how to rebuild the original message from the compressed one. The compression rate, that was the compares the size of the compressed data and the dictionary to the original message to see how much data is being saved. And then this repetition pattern, that's kind of what you were looking for when you were doing this lossless compression, right? This sequence of text that appears multiple times, it can be replaced with a symbol to help us reduce the amount of data that we need. So why are some messages easier to compress than others? The idea here is that, some are easier than others because some contain more repeated text, words, phrases, letters, than other text, right? So the amount of compression changes based on the text that we're looking at, which was, if we're looking at this again, there was a bunch of different text that I could do. The idea, if you were in class, is you would kind of choose one of these and see how well you could compress it. So as a class, we'd choose one, everyone would work on it, and we'd see who got the highest compression rate. Right? Computers are obviously really good at this, so that's really just a way in class to kind of help you guys understand this. Why are other messages more difficult to compress? Again, that's because they just don't have as many repeating patterns, right? And then lastly, what role does the dictionary play in compression loss? This is what makes it completely reversible. This is what guarantees that we lose no data. That dictionary, it's essential because it stores the meaning of each symbol that's used during compression. So without it, the receiving computer would have no idea how to uncompress it. Right? So we have to have that dictionary. Moving on to lesson 10, this is a second form of compression. All right, so not to be confused with lossless compression, this is lossy compression. Lossy compression is a process for reducing the number of bits needed to represent something in which some information is lost, it's thrown away. Lossy compression is not reversible. All right, that's the important thing to know. With lossless compression, it is completely reversible. Lossy compression, it is not reversible. So usually, which form of compression we use is determined by what we're doing with the data. If I am going to take a high-resolution photo and post it on Instagram, I am okay with lossy compression. That computer, your phone, when you see that image, you don't need to reverse it, right? I just need to compress it to a point that it's good enough, right? When you look at it on your phone, it looks nice. It does not have to be perfect, and your phone in no way needs to get that thing back to the original version, the fully uncompressed, high quality version. Same thing like text messages, Word documents, Google Sheets. Those need to be taken back to their original form. We cannot lose data with those, otherwise the message would get lost. So I'm not going to lose lossy compression with documents, with, things that I'm not okay with losing data with. So just understand the difference between the two. There's this term degradation. That's just the loss of clarity or detail in a compressed image. We're going to talk about that. I'm going to show you examples in a second. The compression trade-off is kind of you determining what type of compression I'm okay with and how much compression am I okay with. Right? It's this trade-off, this balance between reducing file size and maintaining an acceptable quality for this image or this song or this video or this text file, whatever it is. And then we get back into that sampling size, which is how large of sections of the image on average, looking at color, how many samples do we want to take, right? Again, this plays into that compression trade-off and the degradation. So kind of looking at this, let's go to lesson 10 and kind of show you some examples here. When we are talking about degradation, compression, sampling size, we have this image here. It's a school bus. Right now the sample size is 1, right? This is our original high quality version. If I change the sample size to 2, what you see is it gets a little grainy, right? It's still okay. I've got some compression going on. My original was, 201,000 bytes. Now I'm down to 51,000 bytes. So it's a good amount of compression just by, moving my sample size from 1 to 2. But you'll see if I go to like 6, right, it starts getting really grainy. My compression is great. I've gotten rid of a lot of data. But remember, this is lossy compression. I can't get that back. If I send this using lossy compression to someone else, this is what they get. They have no way to take it back to this, right? You are stuck with this. So maybe you're okay with that, maybe you're not. Again, that is that compression trade-off. Kind of looking at another example, another way to look at this. This idea that, we have this image looking at different scenarios. So let's just pretend like you're going to send this image as a text message to a friend. Right? Which one of these 4 are you okay with that person getting, knowing that this is lossy compression and they cannot take it back to the original form? I would say if you're just going to text this to a friend, you're probably okay with 2, maybe even 3. Right? This on a phone, I can tell what this is. I know what this image is. I don't care about the details. I'm fine with that. Right? I don't need to get it back here. This other one, you're a crime scene photographer. That one changes things a little bit, right? If I'm a crime scene photographer, there's some detail loss here, and that might be really important to what I'm trying to figure out, so I need to send the high quality version. Right? Again, it just gets into that idea of compression trade-off, degradation, sampling size, right? And then, looking at how much data do I want to use for this. So kind of looking back at your Cornell notes, how is lossy compression different from lossless compression? You should know this one. The idea is lossy compression is different than lossless because it permanently removes information to reduce file size. We cannot get it back. Lossy compression is not reversible. How does increasing lossy compression affect image quality and size? It's going to lower the file size by averaging or removing details, right? But it also reduces the clarity and accuracy of the image, which can make it look blocky, blurry. So it's not a perfect reconstruction, right? When is it appropriate to use lossy compression instead of lossless compression? Again, we kind of talked about this. It's appropriate to use lossy compression when smaller file size or faster transmission is more important than perfect accuracy. So you see lossy compression with streaming all the time, right? When songs are streaming to your phone, videos are streaming to your phone, they are not sending you the original high quality version of that file. They are using lossy compression. They are okay with losing some data. It's going to be good enough on your screen, right? Our human eye really can't tell the difference between the high-end original version and this lossy compressed version that's a little grainier and a little blockier. So lastly, we have lesson 11. This one gets into intellectual property. I'm not going to lecture a lot about this one. Provided, like in these slides, you can kind of see that there are 3 videos on here, right? Again, these slides, they're just 3 different videos. On Canvas, you will see a link to these 3 videos. What you need to do is watch these videos. All right, your project is going to be on this idea of IP, intellectual property, Creative Commons, who owns the data. These videos start to introduce you to that. So there's really no need for me to go into it. These videos do a pretty good job. And it's just to get you to start thinking, like, who owns the data? What is a copyright? What is Creative Commons? Start kind of understanding that. As you go through the videos, you should be able to kind of answer the Cornell note definitions and questions for this lesson 11, but I'll go through those really quick for you. IP, intellectual property, that refers to creative works such as images, music, writing, or code that someone produces and legally owns. All right, so even though it's digital, even though I put it out there on the internet, I still own it. You cannot just take it and use it. Copyright. That's a legal protection that gives the creator of a work exclusive rights to use, share, or sell that work and prevents others from using it without permission. We've all heard of copyright, just make sure you know that definition. Creative Commons, this is a license. So a Creative Commons license allows creators to share their work more freely by granting public permission to use it under specific conditions. So maybe I create a video, I have the copyright for that video. If I create a Creative Commons license, I could, for example, say, hey, any educational institute can use this video free of charge. All right, so if you are a teacher at a school, you now have the right under that Creative Commons license to use that video that I created. Whereas someone in the business world, if they take that video and they use it, I could sue them for that, right? I didn't give anyone access to it. I just gave educational facilities access to it. That's a Creative Commons license. It's an option for, creators of digital work to use when they want someone to be able to use it, but still protect themselves from other people not being able to use it. There's also this fair use. Right? Fair use allows limited use of copyrighted material without permission in certain situations, such as commentary, education, news reporting, or parody. It's just this idea that, like, if I'm a news reporter and I'm going to put a segment on about something, I can use a small section of someone else's work, even if it's copyrighted, just because of the nature of what I do. Right? Because I'm a reporter, a journalist doing this. I can't use all the work. I definitely can't do it to make money, but I can use small snippets of it. It's called fair use. So kind of be aware of that one. So for the questions, why might someone care if their digital work is used without permission? Well, obviously someone might care because they might feel like their creativity's been taken, or their ownership ignored, or their work used for profit without giving them credit or compensation. If you create a video and you put it out there and you find someone else has used your video and they're now making money on it, you're not going to be happy, right? You should be getting some of that money since it's your work that they're using. How does copyright protect creators of digital content? Well, basically, it gives them legal rights it gives them legal rights over how their work is copied, shared, changed, or sold, right? It ensures that others cannot claim the work as their own and profit without that person's permission. That's what copyright does. And then how is Creative Commons license different from a regular copyright? Well, a Creative Commons license Instead of restricting use by default, it allows creators to decide in advance how others can or cannot use their work. So it makes it easier for people to share and reuse materials legally. All right. So again, I know this was kind of a longer video. It was a lot of content. We kind of brushed over a lot of it really quick. So if any of this isn't making sense, make sure you talk to me. Otherwise, just make sure you get this filled in, right? So all your definitions, all your questions should be filled in for 6, 7, 8, 9, 10, and 11. That's your only assignment this week. Make sure you watch these 3 videos. These are short, like 2-3 minutes each. And that will take us to next week. Next week is going to be your assessments for Unit 1. So you're going to have a project and you're going to have a multiple choice test. So again, make sure you come by, do your weekly check-in. If you have any questions, come by and ask me.